the fracture, and we could now differentiate between the type of the fracture, whether it is brittle or whether it's ductile. Okay, there are some characteristic that is known from the microstructure of the fracture. Okay, for example, if you are having ductile fracture, so the represent the sign or the signature of it, of the fingerprint of it, the fracture will be in forms of cups and cones. Okay, cups and cones that signify the occurrence of plastic deformation. Okay, plastic deformation. So if there is plastic deformation, there will be some area that will experience necking. Okay, they will experience necking, and this will eventually break into pieces. Okay, so but if you are dealing with a brittle fracture, so there will be no necking, so there will be no area that would have this uh, shrink, that will shrink. So the from naked eyes, we could see that in a brittle fracture, it is rather a straight line. Okay, a straight line. Okay, or a flat surface compared to the ductile fracture. Ductile fracture have cups and cones, but brittle fracture, they have flat surface. And another fingerprint, or another important feature that you need to state when you are describing the ductile fracture is the dimples. Okay, so you need to mention the word dimples when you are describing ductile fracture. Okay, and for brittle fracture, we could see that there is what we call chevron mark. Okay, chevron mark. I think I have shown to you. You could see at the road, chevron marks, and it is pointing towards the origin of fracture. So you know where is the problem uh, when you are investigating a failure. So you know where to look at. Okay, we know where is the crack coming from. Okay, so more or less we also have differentiate, or we also has classified the brittle fracture into two. Okay, the first one is the intergranular, and the second one is transgranular. Okay, transgranular, the fracture uh, occurs across the grain. Okay, intergranular along the grain. Okay, and the intergranular fracture, I think towards the end of last session, we said that it's sometimes referred to as rock candy. This is the rock candy. So it looks like that, and the surface, when you look at it under the microscope, or under the SEM, you could actually identify those characteristics. Okay, so right, so that is more or less about ductile and brittle fracture. So now we look at we continue the comparison of ductile and brittle fracture. So as you can see right here, okay, Ductile materials show larger area under the stress strain curve, indicating its ability to absorb more energy before fracture, means better toughness compared to brittle material. So when you get SS curve or stress strain curve from tensile test, from you do the tensile test, uh, it give you this curve, okay, this curve. So usually a brittle material, it will be the young modulus will be high, it is stiffer. This slope will be stiffer compared to ductile material, but it will fail earlier. Okay, it will fail earlier. It don't have much strain. Okay, it don't have much strain. So it don't have much strain. So when it uh, when the force, okay, the exerted force exceeded the atomic tensile force UTS, okay, and it start to form voids and breaking. Okay, the brittle material will occur at a very low strain, okay, compared to ductile material, where it will have a very long or very high amount of strain before it would fracture. Okay, so as you can see, this one is stress. Stress is well, if you remember, force over area, right? The strain is well, it's elongation over uh, the initial length. Okay, initial length. So basically this is related to distance. Okay, this related to distance, and this one is related to force. Okay, distance. Okay, distance, and this is related to force. Okay. Oops. Right. So as you know, if you're talking about energy, okay, energy is equal force, energy or work, work equal force times the distance. So the area, okay, uh, show you or represent the energy absorbed from the source of energy, whether it's from tensile machine, right? Before the material fail. Okay, so well, this is translated in the SS curve as the area under the curve. Okay, under the curve. So you can see right here, brittle material, though it is stiff, okay, it is not tough. Okay, tough is referring, okay, toughness referring to the area. If you have a lot of area, okay, you have higher area under the stress strain curve, then your material is tougher. Okay, uh, if it is tough, and it is easier to be break. Okay, so right. So under area under the curve equal to the absorbed energy, ductile materials, okay, which undergone ductile fracture, uh, have very or absorb a lot of energy before it fracture compared to brittle. So that is why we look at this two picture, the real failure that we have. Okay, ductile failure of pipe, one piece and large deformation. You can see that this pipe, I think this should be the welding area. Okay, but it fails somehow. Uh, okay, so the shape, you can see the shape change. Okay, the shape change. Whereas if you look at the brittle failure, okay, if you take each of these, you can actually put that back together. Okay, because the materials itself, okay, it does not change its shape, but rather it directly break. Okay, it directly broke into pieces, and this is not favorable because, as you can see, that it breaks to many pieces. Okay, so it's the procedure or the process to clear it up is also very tedious, and also it is dangerous because it has no warning before it breaks. Okay, so yeah, so to demonstrate that, you can see, okay, the hull, the ship hull, okay, that fracture in ductile manner. Okay, before it break, okay, we can see that it kind of like change its shape. It is deformed. Okay, it is deformed. So people know, okay, that okay, this structure is not safe. Okay, so we can do, maybe we can stop the operation, maybe we can change the component if possible. Okay, we can do some repairing, right, if we are having ductile uh, failure. Okay, um, if on the other hand we have a brittle failure, so we don't have that space, or we don't have that uh, we don't have that warning. Okay, it just happened without without us having the visibility of the failure. Okay, so this is not favorable. Okay, the right hand side is not favorable. This is a more favorable situation. Of course, failure is something that we do not want in the first place, but if it do happen, then we are more inclined to have a structure experiencing ductile failure rather than the materials having a brittle failure, right? So, ductility is a major safety consideration for structural projects. Ductility plays a key role in formability because excessively brittle materials may not be able to be formed successfully. Ductility also shows structure to bend and deform to some extent without rupturing. So, what have we learned? Fracture of metallic materials happen in two stages: crack initiation and crack propagation. This is the first part of our lecture. I forgot to recall this. Okay, the crack initiate and the crack propagate. Okay, two stage of fracture. And ductile fracture is accompanied by severe plastic deformation prior to the failure, while brittle fracture show little or no deformation prior to fracture, and it is therefore more problematic. Ductile fracture is normally preferred. Okay, this is what I mentioned just now, because preventive measure may be taken in as much as evidence of plastic deformation indicate that fracture is imminent and more energy is required to induce ductile fracture than for brittle fracture. Right. So that is all about lesson number one. Okay. Uh, we know in summary, in overall, okay, first thing that I want you to remember is the stages of uh, fracture. Okay, initiation of crack, propagation of crack. Okay, that's the first thing. And the second thing I want you to remember is the characteristic of ductile versus brittle fracture. Okay, that's the second thing that you need to remember. Okay, the characteristic, you have to be able to recognize this. Okay, so if you find some structure, that experiencing failure, please have a look. As a material student, please have a look in it. Try to apply your understanding. Okay, if it is a brittle fracture or ductile fracture. Okay, of course there are fatigue and so on, but that one is later on we're going to look at. Okay, but for now I try to understand the characteristic of ductile versus brittle fracture. Try to remember the characteristic. And the third thing that I want you to know, that why do we favor ductile materials? Okay, you need to be able to uh, explain the thing. Okay, why do we need ductile? Because we need more energy to cause fracture. Okay, that's one thing. And then it occurs, it gives a sign or warning of visibility of the fracture before it actually fail. Okay, so that pretty much wrap up our first lecture. All right, so I'm going to continue to the lecture number two. All right, let's have maybe 3 minutes break uh, for transition. Okay, for us to change our mood. All right. We continue at 10:28. Okay, 10:28. Just 3 minutes. Okay, right. Fracture mechanics. Sorry, I don't know why my screen sometimes become. Okay, okay. Our second lecture. Today, we have a few outcomes from this lecture because it's quite a long one. Okay, until 60. I think we'll not finish this one. We just stop until around 20 slides. Okay. Right. So, first, we want to be able to explain the theoretical cohesive strength and why the strength of brittle material are much lower than the cohesive strength. The number two is to define stress concentration factor KT and its importance. Number three, explain Griffin's analysis of the critical stress for brittle fracture. Number four, explain the difference between three mode of fracture. Next, define what is stress intensity factor K1. And finally, define fracture toughness. Okay. Introduction, brittle fracture is normally ductile materials happen more than we expect. Okay, so just now we have discussed that we favor ductile fracture. Okay, we favor ductile fracture. So when we use when we design, okay, when we choose or select materials, of course, for structural materials, we want to choose the material that is as ductile as possible, right? Without compromising the strength, okay? But the problem is when you expect something to be ductile, but it turns out brittle, that is when the uh, catastrophic event occur, okay? That is when you have a problem, right? So ductile materials can fail like brittle manner under the following conditions. So actually, what's supposed to be ductile material, it can fail like or it can fail in form of brittle fracture. Okay, the materials is ductile, but it can fail in brittle manner. Okay, so what are the conditions? Number one, low temperature. Number two, increased loading rate. And number three, presence of stress concentration. Okay, number one, I think if you have seen the material science class, so there is what we call uh, ductile brittle transition, okay, which occurs in the BCC metals, okay, when you have a low operating temperature, extremely low operating temperature. So there could be the change of um, crystal structure where uh, it will cause the materials to be brittle. Okay, what originally ductile material could change to brittle materials. Okay, increase loading rate if it is too much. Okay, it could have this brittle materials if it is uh, over the yield strength. Okay, at a significant amount. Okay, it could break in form of brittle fracture. And number three, this is, I think we are going to focus on this. Okay, the presence of stress concentration, pre-existing crack or defect. Okay, so when you do a casting, for example, you don't expect the materials to be perfect. Okay, Of course, we want that very close to perfect structure, but there will be some area which will contain crack or defects. Okay, so this is where there will be a concentration of stress, right? So first we look at a very fundamental one, right? Um, Theoretical cohesive strength, as you know, right?